Now we shall be doing the diagnostic checking. That means whether the model is good or not. So go for diagnostic. I'm just right here. We do the diagnostic checking. That is our last job. Diagnostic checking of each model. We have 3 models, right? So we do the testing. Okay, first we have 3 models. One is consumption. This is the first model, and GDP is the second model, and money supply is the third model. First we check about this model. So I make it copy, select. I make it select and copy. I copy it, right? I copy it. I copy and I go to quick and put here estimate equation, and here I paste it. Here I paste it, the whole thing has come up. You can see from here our model has come up. Consumption, all the variables have come here. Can you see from there? It's coming up. Okay. So I need to some adjustment. You can see I put my variable our model here. I can make a zoom for you so that you can see better. So this is my model now. All right, I need to check it. Okay, I need to check whether this model has serial correlation or not. I need to check whether this model has heteroscedasticity or not, and I want to check whether residuals are normally distributed or not. All these things I want to check now, right? For each model. Okay. So I press OK to estimate the model. Okay, here this is the dependent variable consumption, right? And so this is our model. And here what is happening here, you can see from here of this model. Of this model, what has happened? This is model, right? Okay, here what is happening? Only C3 is significant. C3 and C7. These 2 variables are significant only. That means here are 1, 2, 3, 4, 5, 6 independent variable. Out of 6, only one significant. Because C7 is the constant. So actually out of 6, only one variable is significant. So that means the model is not very good, because what is the guideline? Should be majority of the variables should be significant, meaning that out of 6, at least 3 should be significant. That is desirable, at least 3. So here is only 1. So we are not happy about the model. Then R squared is quite low, 53.62%. So that is very low. But the F statistics and corresponding p value, it is significant. So we are happy about it because F statistics is significant. Okay, but the R square is small, but although R square is small, but if the F statistics is significant, then we can accept the model. Although R square is low, but if the F statistics is significant, we can accept the model, meaning that all the independent variables jointly can influence the dependent variable when F statistics becomes significant. So I am telling again, when the F statistics is significant, meaning that all the independent variable jointly can influence our dependent variable. So that is a good news, and that is desirable all the time. Okay, then we have the we talk about test of normality, test of heteroscedasticity, and test of serial correlation. Okay, and so we can do it. I go to view, then residual diagnostic. First I check the serial correlation, right? Whether our model has serial correlation or not. I click here, and here I choose lag 2. Okay, so here is the Bruch-Godfrey test, and I take observed R square and the p-value. P-value is 17.95%, meaning that very high. So I cannot reject null hypothesis. And what is our null hypothesis? Null hypothesis is there is no serial correlation in this model, and we cannot reject it. And that is a good news, and that is desirable, because the probability value is 17.95%, which is more than 5%, right? So we cannot reject null hypothesis. So we are happy about the model because this model does not have any serial correlation. Okay, then we check again residual diagnostic. We check the test of heteroscedasticity. Okay, so we check this one, Bruch-Pagan-Godfrey, and this is the test of heteroscedasticity, and we choose the observed R square and the p-value. P-value is very high, 46.13%, meaning that we cannot reject null hypothesis because it is more than 5%. And what is null hypothesis? The null is there is no heteroscedasticity in this model, and we cannot reject it. That means the model is good because this model is free from heteroscedasticity, and that is desirable. And finally, I check this one, test of normality. I click here. Okay, here the Jarkabera statistics you can see from here, and corresponding p-value. P-value is very small, meaning that we can reject the null hypothesis. And what is our null hypothesis? Residuals are normally distributed, and we can reject it, meaning that residual are not normally distributed, and that is not desirable. So here that is the only one problem, that residuals are not normally distributed. So here we are not happy about the model because residuals are not normally distributed. Okay, so that is the first model. Then we talk about our second model. What happens to our second model? Second model is this model, the model of GDP, right? So I copy it, I copy the model, I select and copy, I go to quick estimate equation and I paste it here. So then I rearrange equation, I set it, I arrange it, Just 1 minute. I'm arranging the models. Okay, so this is my model. You can see from here, right? Okay, I can make a zoom for you. Just 1 minute. Okay, I can make it zoom for you. Just zoom so that you can see the better. It is my GDP model, the second model. Okay, so I can run the model now. Okay, I press OK. So this is our model, and dependent variables is GDP. And here you can see out of all independent variable, I think none is significant. Suppose this one C12, suppose if I choose 10%, yes, in that case it is significant because p-value is 7.23%, which is less than 10%. But if I choose 5%, then C12 is not significant, right? So meaning that we are not happy about it because probably only one variable is significant. And what about R square? R square is very small, 35.86%, and F statistics is not significant because probability value is 10.14%, which is very high. So F statistics is not significant. So we are not happy about this model. Okay, then we check about this one, about the test of heteroscedasticity, test of serial correlation. Okay. So first I check serial correlation test. That I check first. I click here, and here I choose lag 2. So this is the Bruce-Godfrey test. Observed R square corresponding p-value. How much is the probability value? 5.10%, meaning that more than 5%. So we cannot reject null hypothesis, meaning that we accept null hypothesis. And what is our null? Our null is there is no serial correlation. So meaning that this model does not have any serial correlation because the p-value is more than 5%. So we are happy about this model. Okay, then we check whether this model has heteroscedasticity or not. So I check this one, heteroscedasticity, and I choose this one, right? Then press OK. So this one is the test, and observed R square, and the p-value is 53.44%, which is much higher than 10% or 5%. So we cannot reject null hypothesis, meaning that this model does not have any heteroscedasticity. So we are happy about the model. And finally I check the test of normality. It is here. Okay, here the Jarkabira statistics and corresponding p-value, probability value 58.01%, meaning that it is more than 5% or 10%, meaning that we cannot reject null hypothesis, meaning that residuals are normally distributed. So we are happy about this model. Okay, so this model is done. So what about the third model? We check third model. Why is third model? Why is it? Is it here? No, not this one. Our third model is here. Not this one. Our third model comes up here. Okay, it is not here. System equation. Okay, third model is the money supply, right? So I select and I copy as before, then I go to quick, then I do the quick estimate equation, then I paste it. Okay, so I arrange it. Money supply is the dependent variable, and here I'm arranging the whole things. Okay, I take the money supply here. Just 1 minute. I set it, then come back to you. Okay. Okay, it is going on. Okay, then I check the money supply. I just arrange it here. Sorry, have some problem there. It's not coming. Okay, please come. Arranging, taking time to arrange. Sorry, I'm gone. So here you'll have to be careful. Okay, so this is my setting so far I have done. Okay, I can make it zoom for you. So this is the dependent variable is money supply, right? And this is my model. You can see from here, right? Okay, I can run this model now. I enter OK. The result has come up. Dependent variable is money supply, and these are all independent variables. You can see from here, right? Independent variables, and here you can see only one variable is significant, that is C20, meaning that money supply 2, right? So meaning that only one out of so many. So the model is not good. And R squared is very small, 31.3%, and F statistics is not significant. So all are bad. I go to view, then I go to residual diagnostic. I check first serial correlation, and here is 2. Okay, so it is the test of serial correlation. Observed R squared, yes, the p-value is very high, 11.4%, meaning that this model does not have any serial correlation. So we are happy about this model. Okay, then I check the test of heteroscedasticity. So this one I choose. Okay, so test of this one, observed R square. How much is the p-value? 14.26%, meaning that we cannot reject null hypothesis, meaning that in this model there is no heteroscedasticity. So we are happy about this model. Then what about the third one, test of normality? I come here. Okay, here you can see the Jarkabera and the probability. The probability is 7.38%, right? Meaning that it is more than 5%. So we cannot reject null hypothesis. But suppose if I choose 10%, then I can reject it. But Here I'm choosing 5%. In that case, I cannot reject the null hypothesis. And what is our null hypothesis? The null hypothesis is residuals are normally distributed, and we cannot reject it provided we choose the 5% level of significance. So we are happy about it because residuals are normally distributed. Okay, now we have evaluated all the models. We have evaluated all the models, and you know that there are many weaknesses and there are many strengths of each model, right? There are many problems and strengths are available for each model, but we have to make all model perfect. That means there should be no serial correlation, there should be no heteroscedasticity, and residual should be normally distributed, F statistics should be significant, and so on.